Good evening and welcome to the Exploratorium and to After Dark and to this evening's presentation of Everything Matters, Tales from the Periodic Table. How many people have been to Everything Matters before? For those people, you know that we normally hand out cards for each element so you can build up your element cards. Unfortunately, the printer didn't get them to us. So, if you come next month for arsenic, I mean the talk, not the chemical, you will get 2 element cards next month. How many people have been to After Dark before? Oh, that's a good number of people. Excellent. I just want to note that to everybody that we have a special After Dark membership, which if you join will entitle you to come to 52 After Darks, less than $1 a piece. Such a deal. Tonight, we're going to talk about germanium, which is kind of a really interesting element. We're still kind of at the top of the table here. You can see germanium is element number 32 right there. That atomic number is the number of protons in the nucleus of the atom. And we'll start off, we'll go a little history because this is actually an interesting element historically. Even though it wasn't one of the first discovered, our good old friend, Dmitri Mendeleev, the fellow who invented the periodic table, had some interesting problems with his table. If we look at it, here's the way he wrote it down in 1869. Let's zoom in on that a little bit. And there you kind of see the periodic table, except in Mendeleev's version, it's kind of standing up on end and kind of hard to read in this particular version. Let me just make an easier to read version for you here. So this is the periodic table according to Mendeleev. And you'll notice if you look really closely that there's a few elements there that have question marks next to them. Mendeleev knew that they had to be there. There were empty spots in the table where they should fit. Let's take another look at that table. So here's now kind of now put sideways like we're more used to seeing it. And those empty spots, he did not know what those elements were. They were missing elements at the time. But there was this one right here, which was sort of near boron, so he called that one eka-boron. There was another one that was sort of near aluminum, which he called eka-aluminum. There was one near silicon, which he called eka-silicon, and one near manganese, which you'll never guess what he called, eka-manganese, yes. So this was kind of the state of the periodic table around the time of Mendeleev. Let's put it into our version so we can sort of recognize what's going on here. The elements that you see here were the elements known to Mendeleev, and those 4 holes in the table that he couldn't figure out are marked here with question marks. And remember, those were eka-boron, eka-aluminum, eka-silicon, and eka-manganese. Today, we know what those elements are. The first one, eka-boron, what turned out to be scandium. The next one was gallium. The next one was tonight's element, germanium. And the last one, which we won't get to for a few weeks, is a radioactive element, technetium. Now, Mendeleev, because the elements occurred in these groups, could kind of predict the physical qualities of each one of those elements. Let's take a look at his predictions for eka-silicon, or as we call it, germanium. You can see here that he predicted the atomic mass to be 72, and it's actually 72.6. It's pretty close. He predicted the density at about 5.5, and it's about 5.35. He predicted the melting point pretty accurately. Well, he just said it was a high melting point, and it is a pretty high melting point. He predicted the color of the element, and he predicted right on the density of the oxide of the element. So just knowing the elements around it, he could make these predictions, and he was correct. But he didn't have an actual sample of germanium for him to actually do any measurements with. It took another 20 years until germanium was actually refined, and it was refined by this guy, Clemens Winkler, and he was given a sample of a mineral from a mine. This mine was in Germany, and that mineral, there's a picture of the mineral that he got a sample of. It's called are gyrodite. And you can see from the chemical formula down there at the bottom that it's a silver, contains a lot of silver, a little bit of germanium, and it's a sulfide of both of those. And this is not a real common mineral. It's a pretty rare mineral. And he was able, from this mineral, to purify the germanium. And so he was the first one to actually come up with the actual substance. He was going to call it Neptunium after the planet that was just discovered at the time. And he thought that was kind of appropriate because Neptune was discovered by mathematics, and so was germanium, really, because it was mathematically figured out what the qualities were in the table. Neptune, it was predicted by the way that some of the other planets were distorted, had their orbits distorted. But unfortunately, Neptunium was already being considered for a different element. So he fell back on the good old reliable way of just taking your country and giving it the element. So he called it germanium. That mine that the element was recovered from was actually in Germany, and I think I found it. I'm not sure, but I think this might be the mine. It's really hard to find things sometimes, even with Google Earth. There it is right there. That's a mine that's at least near a town that is... they talk about Freiburg. So, as I mentioned, that mineral is not very common. It's very rare. Today, they get germanium from a different mineral, a mineral called sphalerite. And it's really a zinc. It's actually the main source of zinc for that they mine. But it has a little impurity of germanium in there as well. So zinc iron sulfide. They also get germanium from commercially from silver, lead, and copper ores. Again, it's a minor constituent, but it's enough that it's commercially feasible. Germanium is actually a fairly expensive element, unlike the ones we've been dealing with lately, which are, dollars a pound or something like that. Zinc, really, really, really cheap. Tonight, we have a nice expensive element. Tonight's element, germanium, is about 1,000 to 2,000 per kilogram. And that's for not super pure germanium. That's for 99.99% germanium. It's actually refined much, much more than that when you refine it for electronics. So, if you look at the abundance of germanium, it's not the most abundant element. This is a chart showing how abundant it is in the universe. It's the 26th most abundant element in the universe. It's the 27th most abundant element in the sun. It's the 24th most abundant element in meteorites. Getting the feel for it here. Not too abundant, not super rare though. It's the 55th most abundant element in the crust of the Earth, however. So it's fairly rare on Earth. And it's the 42nd most abundant element in the ocean. So it's not a very common element. And as far as us, in humans, it doesn't exist at all. So it's really rare in humans. Germanium, we're now getting up into the periodic table. When you get past iron, things tend to be made in violent ways. And germanium is no slouch there. The only way you make germanium is in exploding massive stars, supernova. So that's kind of exciting. So it's kind of interesting to know that this piece of germanium right here was actually made in a supernova. A lot of you were made in supernova too. But that's the only way that you get germanium. Let's talk about, there's lots of different forms of germanium. I mentioned that there's 32 protons in the nucleus, but there can be differing numbers of neutrons in the nucleus. So there can be different atomic weights of germanium. We call those isotopes. Iso for the same and topes for place. It's the same place in the periodic table, but they're different forms. And you can see here that there are lots of different forms of germanium. There's actually 32 different known isotopes. Now, The number up here, like 63, means that there's 63 total particles in the nucleus. That's adding up the protons and the neutrons. We know there's always 32 protons, always. Just a variable number of neutrons. But not all of these are stable. The only stable ones are these four right here. So germanium 70, 72, 73, and 74. Everything else is radioactive. So these make up almost all of the germanium that we can find on Earth. If you look at that, the most common one is germanium 72. Germanium 74. And the other ones at 36%, and then there's a couple at 20%, 20-ish percent. And germanium, if you add those up, by the way, add all of those percentages up. If you can do this in your head. Got it? It doesn't add up to 100%. It only adds up to 92%. But if those are the only stable ones, that must mean that there's an unstable radioactive isotope that makes up the rest of the germanium on the Earth, and that radioactive isotope is germanium 76. But we're going to talk about that right now. Let's take a look at how radioactive, we'll look at the half-lives of the other isotopes, including that germanium 76. These are all the isotopes that have a half-life that's longer than 1 minute. The rest of the 32 are shorter than a minute. But you'll notice that in this table, germanium 76 has an unusually long half-life. 1.926 times 10 to the 21st years. That's 1.9 sextillion years. That's really long. That means if I have a lump of germanium 76, it takes 1.96 sextillion years for half of it to decay. That's a long time, by the way. That's even this number is too big. That's 140 trillion times the age of the universe. The universe is about 13.8 billion years old. So let's just say that basically all the germanium 76 is still around. So germanium is kind of, as you can see up here, is kind of a grayish, they call it a metalloid, actually, because this is really brittle. If I drop this, it would break like glass. As a matter of fact, if you come up after and look at it, there's a little broken piece on the side here. You can see it has like a conchoidal fracture. It breaks like glass, too. It's a very brittle element. This is the end of a refining. When they refine germanium, they pull it out of a long bath. They crystallize it out of a molten mixture of germanium. This is just the end of a long rod. This is called a boule, and then they slice the rest of it up and use it for semiconductors. In this particular case, so this is just the tailings, really, of germanium refinement. It's actually pretty heavy. You think of these elements as kind of not so heavy, but this one is fairly heavy. It's got a density of 5.3 grams per cubic centimeter. That's kind of middling, actually, among all the densities. You remember what the density of water was? Density of water, 1 gram per cubic centimeter. So it's about 5.3 times as dense as water. So a cup of this would weigh 5.3 times as much as a cup of water. And the other one, you can see I have some down there at the bottom. There's the most dense element is osmium. We won't get to that one for a while at 22 grams per cubic centimeter. Let's take a look. I have, by the way, for those of you who haven't been here before, those of you who have seen this already, I always bring this out. Here's some blocks. Most of them are more or less the same size. So you can feel the differences in density. Come on up after and feel these. I have maple and plastic, but then as far as those are not elements, but they're low density, so I thought I'd put them out there. But then moving from the high density end here, we have tungsten, we have lead, we have copper, we have iron, we have titanium, we have aluminum, we have magnesium way down there, and you can see here where germanium falls. Okay, germanium is it's a fairly hard element. All of the white things here are elements, and the blue ones are compounds. This is Mohs scale of hardness. Anybody who's collected rocks knows this, where the softest stuff at 1 is like talc. You can scratch it with your fingernail. And 10 is diamond. Germanium falls about middle. It's fairly hard. It's you can scratch a lot of metals with it. You can scratch beryllium and molybdenum and zirconium and a few other things, but it can be scratched by silicon and vanadium and things that are higher up. So it's a mids. It's about the same hardness as glass. It has, as Mendeleev mentioned, it has a fairly high melting point of 938 C or 1700 degrees Fahrenheit. And it boils at 2800 degrees C or about 5100 degrees F. So it's pretty high up in the boiling points. Now, another thermal thing that's actually interesting about germanium is if you look at how much germanium expands with temperature, it's fairly low. It's way down at the bottom down there. It only expands by 6 millionths for every degree centigrade you raise it. Sorry, I keep saying centigrade. I should say Celsius. I'm old. The aluminum expands about 4 times that much. And if you look, the very top one here, I don't know if you can read it way back there, but the top highest expanding element is mercury. And mercury expands about 30 times as much per degree Celsius that germanium does. Germanium's really low expansion rate. That means that molten liquid germanium would be terrible in a thermometer, but mercury, because it expands so much, is really good in a thermometer. Alcohol, you can't get mercury thermometers anymore. They're illegal in the United States, but you can get alcohol thermometers. Alcohol actually expands about 180 times as much as germanium. Okay. It has a moderately larger atom, bigger than hydrogen. And because it has 4 electrons hanging out, doing nothing. And those electrons kind of make the atom a little bit bigger. We'll talk about that in a moment. It has some nice lines in the spectrum. You see all the bright lines here. This is the spectrum of germanium, so you can identify it spectroscopically. I usually try to show the sun's spectrum, except the sun doesn't have enough germanium to actually have any lines in it, so I can't show you the sun. But one of the most interesting things about germanium is that it's a semiconductor. There's a few elements here that they don't conduct electricity very well, but they're not good insulators either. And that's those ones in blue there: boron, silicon, germanium, arsenic, antimony, and tellurium. Yes, I got that right. Okay, I have to memorize all those symbols there. If you look, I mentioned that germanium has 4 electrons kind of waving out in the breeze that would like to combine with something. So here's kind of a germanium atom. So germanium atoms, if you in a block of germanium like this, kind of join up in a kind of a arrangement like this. And if you look at a giant block of germanium, there you see it, and all of the atoms have their outer 8 electrons full, which means they feel good about themselves. They kind of feel like a noble gas. But if you have a block of germanium like this, since all of the electrons are kind of occupied in the bonds, and say you connect a battery to it, you would notice that even though it's a semiconductor, it's a very poor conductor, so you really wouldn't get any current flowing through that. We can make germanium into a conductor, and the way you do that is you add some impurities into the germanium. So for instance, take phosphorus. Kind of looks like germanium, except it has an extra electron hanging out here, an extra valence electron hanging out here. And so if you take your block of germanium and you just add a few, you don't have to add many, one in a million atoms, and you kind of throw those atoms in there, those extra phosphorus atoms, you can see now there's electrons that aren't doing anything. They can actually participate in conducting the electricity. Now, because there's extra electrons hanging out here. There's extra negative charges hanging off of each one of these phosphorus atoms. This is called an N-type semiconductor for negative. And if we connect a battery to it, we would notice that a current would actually flow. This is now a conductor. Well, not only can we add negative things, impurities, but you can also add things like boron. Boron only has 3 electrons in the valence electrons hanging out. So if you add a few extra borons into here, now you've got positive sites. Now these are, again, uncoupled. These are actually make this thing conductive. These aren't N's, these are P's, so this is called a P-type, they're positive. So it's a P-type semiconductor, and this, adding those few atoms of boron makes this conductive. So you attach the battery, and you would find that this also conducts electricity. Now that's not too interesting or spectacular, but if you take the P-type semiconductor and combine it with an N-type semiconductor like this, now we have 2 of these things sitting side by side, and there's a junction between the 2 right here. Now what happens when you join the 2 together is the negatives attract the positives attract the negatives, and what happens is they kind of switch places there, and you end up in the middle. See, there's things there that aren't charged at all. They're happy. There's no positives, there's no negatives. That is kind of an insulating region. It's called a depletion zone. You've depleted that zone of all of the charge carriers, the things that allow it to be conductive. Now, if you hook a battery, let's try it. You can hook a battery across this thing. And if I hook it up this way, so the positive end is connected to the N-type, and the negative end is hooked up to the P-type, you'll notice that the positive charge in the battery is going to attract the negatives here. Watch what happens. And they move farther away. Also, the negative end of the battery is going to attract the positives. Opposite charges attract. And they move farther away. Look what we've done. We have made the depletion zone bigger. The insulation has gotten better. So no current is going to flow here. But let's take the battery, let's take the battery off, and let's connect it the other way around. So now the negative side is hooked to the N-type, and the positive side is hooked to the P-type. If you do this, let's follow what happens. The positive charge on the battery is going to repel the positive charge in the P-type semiconductor, pushing it into the depletion zone. The negatives on the negative side of the battery is going to repel these negatives and push them into the depletion zone. And what does that do? It reduces the depletion zone to 0, and now a current will flow. So in this device, in one direction, the current won't flow. In the other direction, the current will flow. This device only allows current to flow through in one direction. We call this a diode. It's a very important electronic component. The first diodes were made out of germanium. And here's a kind of a photo. There's a very close-up. This right here is only like 1/8 of an inch long. So these are very small devices. Now that same principle can work and does work to turn light into electricity. On our roof, we have 5,874 solar panels, but they're not germanium. In our case, they're made out of silicon, which was a few elements ago. And silicon photocells are sensitive to, this is the amount of light the sun puts out from ultraviolet over here to infrared over here. There's the sun's output. And here in this greenish region is the response of silicon solar cells. So silicon works from barely in the ultraviolet to a little bit out into the infrared. And we generate hopefully, eventually, we're going to generate all the power that we need for the Exploratorium from our roof. If you look at germanium, germanium has a different place where it's sensitive to light. It's sensitive to light more in the infrared. Now this is a different kind of solar cell I'm just showing you here. This is called a multi-junction solar cell. It's layered with different layers of things that are sensitive to different colors of light, which means it's more efficient. If you can turn more of the sunlight into electricity, that's a good thing. Silicon solar cells, like the ones on our roof, can turn about 20% of the light into electricity. If you layer things together, these are much more complicated and expensive to make though, you can turn up to about 30% of the light into electricity. But, as I mentioned, these are very expensive, but you'll notice that, and here's why I brought up the whole solar cell thing, is in a multi-junction solar cell, germanium is in the lowest level, and that's what is the green here. It's actually helping the more infrared can be absorbed and turned into electricity. These solar cells are too expensive for the roof of the Exploratorium, but they're not too expensive to put on spacecraft, where you want to generate more electricity with less weight. So you have fewer solar cells. That diode, that PN junction device, actually is the first step in a much more interesting set of devices, which were invented by these guys. This is John Bardeen, William Shockley, and Walter Brattain. And they invented in 1947 at Bell Labs in Murray Hill, New Jersey, they invented the very first transistor. The transistor is kind of a similar device to a diode. And by the way, yes, they got one of those, the Nobel Prize for that. Right here, I do have a model. This is a model of their very first transistor. And this is a true size model. So there's a model of the very first transistor. It's pretty big compared to transistors nowadays. Actually, here's a close-up of it so you can see. There's a triangle of, well, here's a triangle of plastic. On this side, there's a little piece of gold. On this side right here, there's a little piece of gold. And you can see here, there's a little slab of germanium right there. Well, let's look at it kind of more diagrammatically. This slab of germanium has the top side is a P-type semiconductor, germanium, and then it's sitting on top of an N-type. So we have a PN junction right there, so that could be a diode. But what they did was they put this metal triangle with the gold on this side, the gold foils on that side, on the plastic, and they connected wires to one gold foil, the other gold foil, and to the base. What this does is it makes a switch for you. If you put a very small current in right here, you can make a bigger current flow through here. You can amplify the current, or you can switch on and off a large current with a very small current. That was a really, really important invention, because before that you had to do it with vacuum tubes. And you can see even the very first transistor is smaller than a vacuum tube. Here's kind of the symbol for it. There's a little triangle coming down onto the base. So you put a little current in here, and a big current can flow through here. They kind of look like this if you see the actual devices. They come in all shapes and sizes. This metal can one was kind of an earlier version of the transistor, and these are the more modern versions, power transistor. And there's two types of transistors, depending on whether you want to supply the current or you want to drain the current from something. You have PNP transistors and NPN transistors, and they really both kind of do the same thing. But they have different symbols in case you want to know that. That power transistor, here's kind of a modern power transistor. It's pretty hard to see the P and the N and the P here, or the N and the P and the N, whichever this is. But the chip is right there. This is a very large piece of well, in this case, probably silicon. Most transistors are made out of silicon nowadays. And this is in an exhibit that you can find here. We have an exhibit that's called Transistor. And now this is a really interesting exhibit that was built by an artist named Tim Hunkin. I hope that if you haven't seen, Tim Hunkin's did a series of television shows back in the 70s called The Secret Life of Machines. Look it up on YouTube, it's awesome. But in this exhibit here, you put one hand here, you put one hand here, and a tiny current flows through you and into the base of the transistor, and that allows a very large current to flow through the lamp. If you put this amount of electricity through you, you'd be laying on the floor. But this lets you use a small amount of current to control a large amount of current. So your job is to find that exhibit on the floor. It's somewhere in the South Gallery on the other side of the museum. Transistors have been made very small. So small that in, like my current phone that I just bought, a brand new phone, this phone contains a chip, a processor chip, and that processor chip contains, just in my phone contains almost 7 billion transistors in the chip that's the size of my little fingernail, actually smaller than my little fingernail, in my phone. That's amazing. Okay, I think I'm back on. There we go. Another use of germanium, and one of the major uses, about 50% of the germanium, actually about 25% of the germanium is used I'll tell you about that in a moment. About 50% of the germanium is used in fiber optics. Fiber optics allow you to take light at one end here, and this is just a big plastic rod, so that's kind of a demonstrator. That's not really a fiber optic, but light comes in one end and it bounces off the sides here, and then eventually the light reaches the other end. True fiber optics look like this, or here I have one right there. So inside of here there's a glass fiber, and the germanium helps the glass fiber contain the light. There's just a little bit of germanium that's like, remember when we put the phosphorus and the boron into the germanium, it's doped. There's just a little tiny germanium in the glass here, and that makes the glass more, it bends the light better. So in this case, I can take my laser here. Let's see if I can do this. You need like 3 hands here. Okay, so you guys look at that end of the fiber, and I'm going to put light at this end of the fiber. Can you see light coming out of that end of the fiber at all? This fiber here is about the thickness of a human hair. Very, very thin. And this is used for data communication. This is used all through the Exploratorium to get our data from one end of the building to the other. There's just a patch cable, though. This is not the cable that we use to go a long distance. This glass is so clear, light will pass through 10 kilometers of this fiber and pretty much be the same brightness at each end. That's pretty amazing. That fiber looks sort of like this on the inside. This is just showing 2 different kinds of fiber. This one, the light just bounces off the inside, but here, they change the bendiness of the fiber. In the center, it's more bendy, and the outside is less bendy. So here, the light kind of curves through the fiber, and that's where the germanium gets used, is in this, it's called a graded index fiber. Now, about 50% of the germanium is used to make fiber optics. About 25% of the germanium is used in optics. So here, for instance, in this box, I have a germanium lens. You look at this and you go, well, that's not convincingly a lens. It looks more like a mirror, actually, doesn't it? I can flash you all in the face, yes. I could put a 1,000 lumen flashlight. I'm not going to shine this in your eyes, but except I do this. Do you see any light coming through at all? No, you do not. This is not a lens for visible light. This is a lens for infrared light. This will focus infrared light. I have another example here too. By the way, at $1,000 a kilogram, these lenses are really expensive. Here's another germanium lens. Again, no visible light would come through here. This is loaned to me by a good friend who has the most awesome element collection I've ever seen, Ethan. He's a good friend of the Exploratorium, former explainer. Support the explainers. I took this lens here, and I brought it over to our infrared camera, and I held it in front of my face. Check it out. So, is this transparent to infrared? Watch. It's like a window to infrared. And that was this lens right here. You can come up and check this out. I know, it's kind of like a romper room thing, huh? This germanium can be ground into shapes and can focus light. And so infrared cameras use germanium optics. I have an infrared camera right here. This one actually is kind of cool. This one's made by a company called FLIR. They're kind of the 800-pound gorilla in infrared cameras. This one, you can buy a camera. It actually goes onto your iPhone or your Android and lets you have an infrared camera that you can go around the house and look at where heat is leaking from your house or whether your thermos is working properly. So one last, I think this is the last thing I have, is that germanium is also used as a scintillator. When a cosmic ray or a radioactive particle, a gamma ray, goes through germanium, it gives off a pulse of infrared light. You can detect that pulse. And the size of that pulse tells you something about the energy of the gamma ray that went through. So if you listen to the, we'll turn this up, if you listen to the, are we okay with that? Oh, do I have to turn up my sound here? No, you should be here. There we go. This is if you could listen to it, this is what you would hear. The output from a germanium crystal being exposed to a low source of gamma rays. You get some big spikes, and you get small spikes. Now, every teacher knows how to make a histogram, right? You have A students and F students, and you have the C students in between them. Well, you do the same thing with these. Think about the height of these pulses and make a histogram of them, and you get something out that looks like this. This is the energy of the gamma ray, and this is how many there are of them. And you'll notice that, for instance, cesium-137 has a big spike of gamma rays just at that energy right there. As a matter of fact, you can identify radioactive elements by looking at the spectrum of the energies of gamma rays, and you can actually buy one of those instruments. This is kind of the cheapest one I've ever seen. And this has a little, I think it has a little germanium sensor in it. You hook it up to your computer and you could take gamma ray spectra. I don't know if that's useful to most people. We're about to add one maybe to our suite of instruments on our roof, so we'll be able to see if the environmental gamma radiation changes. So if there's a nuclear accident somewhere, we might be able to see that. So we're going to add that fairly soon. It's a UC Berkeley program that we're hoping to participate in soon. Okay, biological. Germanium has no biological use at all. There is no biological function in animals or plants. I don't have to say anything more about it then. So that leaves us only with our monthly haiku, elemental haiku from Mary Soon Lee. So by the way, there's about, silicon has taken over completely for germanium now, pretty much, except in optics and fiber optics. So the haiku today is, do you miss it still? The semiconductor crown that silicon stole. Next month, we're going to be doing the deadly element arsenic. It's only deadly if you eat it. And that'll be on November 15th at 8 p.m. I also do another set of talks here that are called Full Spectrum Science. This month, we still have all the Full Spectrum Sciences to go. On next Thursday at 8 p.m., we're going to talk about science fiction and science fact. You want to know where that flying car is that you've always wanted, or that rocket pack? You should come and find out. Also, on the next Sunday, October 28th at 1 and 3 p.m. So that's all I have. Thank you very much for coming tonight. Enjoy the rest of After Dark.